Hello everyone, welcome to this video. In this video we are going to discuss about the LEDs and their materials. Okay, here after completing this short video, I hope you will be answered to these two questions. The first one is why not silicon or germanium are used to manufacture LED, and second one, then what are the materials we are using to manufacture LED. Okay, so here the materials can be classified into two types. One is direct band gap materials and another one is indirect band gap materials. What do you mean by direct band gap materials means? Look at this graph. In this graph, if you consider the energy versus momentum, here conduction band and valency band, they are having their peak values at the same momentum. It is known as direct band gap materials. But by nature, no materials having this structure. For example, if you consider the silicon which is having its valency band, its peak at K1 and the conduction band, its peak at K2. They are not in the same point, so that it is an indirect band gap material. Okay, so here if you come, no materials are direct band gap materials, but by combining different materials we can produce the direct band gap materials. So direct band gap materials only we can use to manufacture LEDs. Okay, so here if you consider the group 3 and group 5 materials, they are having same lattice point at certain conditions, so that we can combine group 3 materials and group 5 materials to produce direct band gap materials. Okay, so here energy band gap is decided by the wavelength. Okay, so here lambda equal to 1.24 divided by Eg. Eg in terms of electron volt and lambda in terms of micrometer. Okay, so here mole fraction of the materials decides the energy gap. For example, if you consider gallium aluminum arsenide, in that the equation Eg equal to 1.424 plus 1.266 plus 266x plus 0.266 x square decides the energy gap. Okay, so if you take x value, that is nothing but aluminum mole fraction. Based on that aluminum mole fraction, we can decide what is Eg. Based on Eg, we can decide what is lambda, aluminum wavelength. Okay, so next one, for indium gallium aluminum arsenide, Eg equal to 1.35 minus 0.72y minus 0.12y square. In the same way, aluminum mole fraction decides the energy gap, and the energy gap decides the wavelength. Okay, look at this table. In this table, we are having different material combinations with different colors. Okay, so if you we know that in electromagnetic spectrum, the visible range is 400 to 750 nanometer approximately. Okay, this is a range. Okay, so here 400 it starts from violet and 750 it ends up to red color. In between we are having different colors. Okay, so how we can decide the colors of the LED means with different combinations. Okay, so here in this, first look at this material, indium gallium nitride, okay, which will emit ultraviolet colors and blue green. Okay, for ultraviolet, which is less than 400 nanometer, for blue 450 to 500, for green 500 to 570. Similarly, if we consider aluminum gallium indium phosphide, which is able to emit yellow, orange and red. Yellow range is 570 to 590 nanometer, orange is 590 to 610 nanometer and red is 610 to 760 nanometer. And then gallium aluminum arsenide. Gallium aluminum arsenide can able to emit red and infrared. The range for infrared is 760 nanometer. Similarly, for gallium phosphide, green and yellow. Green color range is 500 to 570 and yellow is nothing but 570 to 590. Okay, so now these materials can be used to manufacture LEDs with different colors. Okay, for example, if you consider gallium aluminum arsenide, in which I will combine gallium arsenide and aluminum arsenide with certain ratio. That ratio is nothing but aluminum mole fraction X. Okay, so which decides the energy gap. Okay, so by selecting certain X value, aluminum mole fraction value, for example, I am selecting some X which will give me this equation. Eg is nothing but 1.24, means lambda equal to 1.24 divided by 1.24, that is equal to 1 micrometer. 1 micrometer is nothing but 1000 nanometer, which is beyond the visible range, so that it is infrared LED. Okay, thank you.